The place where you get the most use out of the standard deviation of a random variable is when you have n, which is just some number of independent and identically distributed random variables. So if we find x is the outcome of one such random variable, and we have n of those, and they're all sort of the same, then the expected value of n times x is n times the expected value of x. And the standard deviation of n times x is equal to the standard deviation of x as a quantity times the square root of n, which is an interesting result. But putting these in words is a little difficult. It's easier to understand this in an example. So let's take this random variable. X is the sum of 12 d6. So in this case, n is 12. We have 12 d6s. They're independent and identically distributed because we assume die rolls are always independent. They're identically distributed because every d6 has the same probability distribution. So the expected value is just going to be 12 times the expected value of one of those dice. So the expected value is, and we know we calculated this before in the example with the young green dragon, 12 times 3.5 gives you an average of 42 on 12d6. Now the standard deviation is similar, but it's a little more complicated. We're going to do the standard deviation of 1d6, which we saw previously was about 1.7078. So we take 1.7078, we multiply that by the square root of n. In this case, n is 12, so we multiply that. So we get about 5.92, let's say. So the interesting thing, as we touched on before, if we're talking about 12d6, that's going to be very close to a normal distribution. Not exactly, because the normal is continuous, meaning any decimal number is allowed. And here, really, if you roll 12d6, you can only get discrete values, whole numbers. But it's approximately normal, so we could model this with an approximately normal distribution with a mean of 42, a standard deviation of 5.92. And you could even go into GeoGebra and put that in. Go to your normal model, put in a mean of 42, and a standard deviation of 5.92. And this was the poison gas damage that the young green dragon's breath does. It has an average of 42, a standard deviation of 5.92. So, you could apply things like the 68, 95, 99.7 rule to that. But, you can see that doing as little as 25 damage would be pretty unlikely, but anywhere between, the low 30s to the high 50s would be sort of expected. As another example, let's suppose there's a game show that pays out an average of $2,100 per episode with a standard deviation of $900 per episode. There's lots of game shows that have payouts, everything from Jeopardy, Wheel of Fortune. There's that one Deal or No Deal. Even a lot of those courtroom dramas or reality courtroom shows, they're not really real courts. The show pays the settlement, whatever it is, because it's just entertainment. It's not meant to be legally valid. But you might want to know what are the mean and standard deviation of the amount given out over 30 episodes. If there are 30 episodes, for example, in a season, then you know the average for each episode, you know the standard deviation for each episode, but the mean you calculate just by multiplying $2,100 per episode times 30 episodes. That's not super complicated. You get $63,000. And then the standard deviation, you just take the standard deviation per episode, multiply it by the square root of the number of episodes, and you get, if we format this as currency as well, so you get $4,929.50. So this gives you an idea of not only the average amount you're going to be giving out over a season of this show, but also some idea of the spread. So you could use those outlier rules, like the 2 standard deviation rule we looked at in Module 1, to try to see, like, what would an outlier be in this kind of thing. And in this case, an outlier would be a whole season of this show. You kind of get an idea of what's the expected range or what's the total amount you plan to give out over a season. You don't need to use this a lot in this class, but I certainly think it's interesting, and it does come up in enough context to get an idea. And this whole idea about the square root of n showing up in formulas appears in a lot of formulas when we look at larger sample sizes and standard deviation.